record on this computer. We have two 10 nanocoulomb charged particles are 2 centimeters apart on the x-axis. What is the net force on a +1 nanocoulomb charge midway between them? So the way that I have tried to recommend to you guys for every problem that we've done since we started was to get on the page, what do we know, before we start trying to solve an equation. And at least this is the way that I do these problems. After many years, I still have to do this. I'm not lying to you. This is the most helpful way that I have to do this, is you convert this word problem into some kind of set of knowns and unknowns. What do we know? We know that Q1 is +10 nanocoulombs. We know Q2 is +10 nanocoulombs. And Q3, which is the one where we want to figure out the force on, is 1 nanocoulomb. Here, in this abstract notation, the J would be the 3. This is the point where we want to figure out what the force is. These velociraptors are starting to kind of weird me out, so I'm going to try something else. They're scaring me a bit. So how about just, how about that? Is that not too disturbing? I don't know.
It's boring, but it's not disturbing.
It's boring. Okay, so we want. How about a picture of my new rescue pup? Should we leave that up there? This is Bo. We just got him yesterday. He's happily playing with the girls upstairs. We're getting yes, leave the dog. Okay, so this is Bo. Bo Slifer is the newest member of our family, and we'll leave him there. And midway, you might have seen me talking to somebody off screen. I've been informed that Bo has left a deposit on the rug upstairs that I have to clean up after this lecture. So what do we know? We have +10 nanocoulombs, we have +10 nanocoulombs, we have 1 nanocoulomb in the middle, and this J is where we want to calculate the force. The R, right away, if I didn't think about this, I would say, hey, R is 2 centimeters. But I'm going to say, let's pause on that, draw this out, and see where that R is before we jump right in. The other piece of information that is useful to me as I'm doing this is to remember that the N in this NC is nanocoulomb. It's SI, and that's 10 to the minus 9 coulombs. So you want 10 to the minus 9. K is this Coulomb constant, 9 times 10 to the 9, with these horrible units that work in Coulomb's law to get you in newtons in the end. Newton meters squared per Coulomb squared. So this is what we know, and then it's asking me, what is the net force? So I'm going to have to figure out the force of each of these charged particles on the charged particle in the center. Now let's get to drawing this. So I'm going to have a 10 nanocoulomb particle here, a 10 nanocoulomb particle 2 centimeters away. And I haven't drawn it here right now just for simplicity, because I want to break this down into manageable bite-sized bits that I can deal with. The idea is to figure out the net force on this Q3. So I'm just going to do one of these at a time. And I have 10 nanocoulombs here. I'm told that the Q3 was placed in the middle of them. In the middle of the 2 centimeters is actually at 1 on that x-axis. This is a one-dimensional problem. So if I had done this a little bit quicker, I might have thought, hey, the distance is given to me as 2 centimeters. No, but if I draw it out, I actually realize this guy's in the middle, and my distance is going to be 1 centimeter. So I go back to, now I have everything I need to start calculating Coulomb's force. So K is just that constant. The charge between the charges, one of them is going to be 10 nanocoulombs. That's 10 times 10 to the minus 9. And then this guy has 1 times 10 to the minus 9. And the distance between them is, again, we have this kind of awkward notation as we have multiple particles. So the distance, I have to discriminate between the distance between 1 and 3 and eventually 2 and 3. So I've given this subscript 1, 3 here. And the last place where I can make a mistake is if I don't do SI. So I want to put this in SI, and 1 centimeter is going to be 0.01 meters. So I have everything I need now. Again, I'm being a little bit lazy here. I put the meters there, but I didn't put all the other units. But I know in my head, I did my due diligence up here, and I put everything into SI units. So this is SI units of Coulomb, Coulomb. This is my Coulomb's constant in SI units, and this is in meters. So I know in the end I'm going to get SI units, which is newtons there. So if I put these numbers into my calculator, I get 9 times 10 to the negative 4 newtons. That's the first part of our problem. It just gives us the magnitude. Again, we go back to Newton's, not Newton's, Coulomb's law. Do I have it here somewhere? Coulomb's law is going to give us the magnitude of the magnitude of the charge, and then to figure out the vector nature, the direction of it, we have to figure out, are they the same charges? That's going to give me a repulsive force, or are they opposite charges? That's going to give me an attractive. So let me move up here to our problem. And because these are both positive, they are going to, want to get away from each other. They are going to repulse. And I know that repulsing in this sense means that this guy is going to be, whoops, turned everything blue. This guy is going to be pushed to the right. So I know that 9 times 10 to the minus 4 newtons is repulsive. It's going to be pushing to the right. Okay, I hope that's okay. I'll monitor the chat just here for a second, but I think people are okay with that. So let's, that's half of our problem. You notice that I'm trying to break this up into bite-sized chunks. I really honestly do this when I solve these problems, and I really honestly hope that if you struggle with it, hey, if you are able to do this, just off the top of your head, then awesome, and congratulations. But when I do these problems, I do break them up into little bits. Otherwise, I get them wrong, even after doing these after many, many years. So the other part of this problem was we're trying to figure out the net force on Q3 due to Q1 and Q2. So now I have to look at I've already done the force due to 1 on 3. That's this arrow right here. The force on 3 due to 2 is going to be now the next part of this problem. I go back to Coulomb's law. I put in Q2 and Q3. Again, this is going to be 10 and 1. And the distance is symmetric. But again, it's going to be 1 centimeter. So I put that 0.01 in the denominator. And I get the same number, which is probably not, this is, after a while, you can develop some intuition on these problems. If I had a 10 nanocoulomb charge on this side and a 10 nanocoulomb charge on this side, everything is symmetric. So the magnitude is going to be the same. You could have actually done this intuitively, but until you've practiced these a little bit, I wouldn't recommend to try to jump ahead like that. The magnitude is the same, 9 times 10 to the minus 4 newtons. And now repulsive, right? So repulsive means that they're pushing away because they're like charges. But the difference now is we're thinking about these two charges being repulsive, right? And now that means that this guy would tend to float this direction. It would want to get away from Q2. So repulsive in this sense gives me a force in that direction. So now my 9 times 10 to the minus 4 newtons is pointing in the left direction. I go back to this abstract equation that I started with, and I just put in my numbers. The vector nature of this, the arrows are the plus and the minus, is taking account of that. And I have 9 times 10 to the minus 4 newtons to the right, which is a positive, minus 9 times 10 to the negative 4 newtons to the left, that's my negative, and that's equal to 0. So again, you could have maybe intuitively seen what was going to happen here just by thinking about, hey, this is symmetric. And that's a very powerful way of looking at physics, but you have to kind of develop that intuition a little bit by doing the hard work first. So I hope you see that after the fact, but I don't recommend, using that right away until you feel a little bit more comfortable with these problems. So if that's okay, I'm going to complicate this even more. If not, I'm happy to explain anything more about that problem. So now, how about if Q2 is negative 10 nanocoulombs? So what I'm doing here is it's the same problem, and now hopefully you see it's not as complicated as when we first started. So I'm not going to do it as piecemeal as before. We still have plus 10 nanocoulombs here. We now have negative 10 nanocoulombs here. In the middle, I still have this 1 nanocoulomb. So it's a similar problem, but I've changed Q2 to be a negative. So Q2 here is negative 10 nanocoulombs. So F1 on 3, if I ignore this guy and focus on the interaction between these two, Q1 and Q3, F1 on 3 is going to be the same as before. Nothing's changed at all. So I know exactly the answer there. It's the same number I got the first time, plus 9 times 10 to the negative 4 newtons to the right. And F2 on 3, well, if I go back slowly here, bear with me so I don't get you seasick by scrolling too fast. If I go back to Newton's law, I keep saying Newton's law, I'm very sorry, it's Coulomb's law. If I go back to Coulomb's law, well, the magnitude doesn't care whether this is a plus or minus. So even though I've changed that 10 to a negative 10, I'm still going to get the same magnitude, right? So F2 on 3, again, in this awkward notation, that's the force that 2 is exerting on 3. The magnitude is the same because the number 10 is the same, although I've changed it to a negative. But the direction now has changed. I now have a positive and a negative, and they want to be brought together like that. And what does that mean when they are brought together? It means that now 2 on 3 is going to be pulling 3 in this direction. So the direction has changed. It's now both of these forces are pointing in the same direction to the right, and they add. So the net force is 9 times 10 to the negative 4 newtons plus 9 times 10 to the negative 4 newtons, and that's equal to 1.8 times 10 to the negative 3 newtons in the positive direction. The sum of those two forces, if I put it graphically up here, would be twice as long as each of these individual forces, because you remember from the first semester, that's how you graphically add vectors. Okay, so any questions on that, or we're okay? All right, so the thing that I'd like you to do, and I will post this as part of the notes so you don't have to find it, but I'd like you to read example 20.6. It's in the textbook for the people that have the textbook at home. It's called What is the Force Between Bees? It's on page 709, and I will actually post the content of that example. But I think it's a nice example of, how this type of force is, what it means to these, to a real biological system. So we're getting a little short on time, so I won't spend too much time on this, but I'd like to just put a little conceptual problem up here for you. We're still having some technical difficulties. Yes,
can I interject here?
Yes.
So in the 8 a.m., we couldn't do polling. If people can private message Carl their answer so that your answer doesn't influence other people, I think that would be the closest to private polling that we could do.
Okay. You guys know how to do that, I hope. Anyway, we'll try.
You can try.
So we're going to do, yeah, that's true. Like the choices that were made kind of influences everybody else's choices. So the statement of this problem, we have two charges, Q1 and Q2. The charge on 1 is larger than the charge on 2. We know that since they're both positive, they're going to exert a repulsive force. If Q1 is equal to 4, if the charge on 1 is equal to 4 times the charge on 2, which of the following statements are true? So we have some 2 units of charge on this guy and 8 units of charge on this guy. There's 4 times more charge on this one than there is on that. If I am to look at the forces on both of these objects, how do I compare them? is F1 on 2 bigger than F2 on 1? Are they equal, or is F1 on 2 less than F2 on 1? We'll give you a little bit of time to think about that. And for me to cough.
Carl, are you getting some answers?
I am getting a ton of answers, and it's hard to keep up with the chat here. So let's shut this down. Thank you very much for everybody. So I got a lot of A's. I got some B's and hardly any C's. So can I pick on anybody here who picked a B? I'm going to pick somebody randomly out of the crowd. I hope you are not. If you don't like this, then just ignore it. I'll wait 5 seconds and I'll pick somebody else if you don't want to talk. But Stephen Morena, you chose B. Would you be willing to explain to the rest of us audibly why you chose B?
Sure. So in the end, you're multiplying the Q1 and Q2 forces together when you're solving for force for either one. So because of that, you're basically multiplying both the equations, both the force equations by, in what is a sense, 5Q. So in the end, they're going to be equal since they have the same equation to solve for both of them.
That's okay. Yes. I'm not sure if I follow you the part where you said 5, but I do follow what you're saying there with the equation, 1 on 2 and 2 on 1, you're basically going to get something similar. And right here, I think is what Stephen is guiding us to, that basically the magnitude is going to be the same because Q1 and Q2 are going to be the same in those two equations. There's another thing that we could fall back on here, which is, first semester rules still hold, and Newton's third law, the law of equal and opposite forces, still does hold in the electrostatic region. It was taught to you in the context of classical mechanics, where we're usually talking about something hitting something, like you punch someone's face and their face punches you back just as hard as you punch them. That's why you can kind of break your knuckle when you do that. But this concept carries over to electrostatics, that the forces are going to be equal and opposite. So thank you very much, Stephen. And for the rest of you, I hope that helps explain. And we'll try to get this polling up and running a little bit better next time. So the last thing that I want to introduce, and I'm running real late on time, so I feel bad I'm going to have to rush through this, or maybe we just won't finish it. But Coulomb's law tells us how to find the force exerted by a charge, by a source charge on another charge some distance away. So this force equation, KQ, Q over R squared, it's the same equation. I'm just simplifying it a little bit by taking off those absolute value bars and changing Q1 and Q2 to a big Q and a little q. I hope that's not too big of a stretch for you. Same exact equation. I'm thinking about, hey, I have a source charge here, big Q, and it's influencing, it's exerting a force on this charge over here. But there's an age-old question that arose, in physicists in the early days and really bugged people and bothered people. And the question is this: these two charges are separated by a distance in space. How does this little charge over there even know that there's a big Q over there? They're separated in space, and there's the term for this is spooky action at a distance, and it really bothered the founders of physics, and it took a long time to kind of come to peace with this. I'm going to introduce the concept today, and hopefully we can delve a little bit more deeply into this and talk about numbers as we go. But the concept is this idea of an electric field, and what we envision is that this source charge alters the space around it in some physically real way, and that modification of the space around it is then picked up by this charge over here. So it's we've introduced a middleman in this, whereas before we had these two interacting by a force. We now think of, or I'm asking you to think of this conceptually as this big Q alters the space around it in some weird way that then this Q, when it's sitting in that space, is going to behave or feel a different effect than if it hadn't been modified in the first place. Please bear with me. I get that this is abstract and a little bit weird. And I'll try to walk us through this so that we can kind of get some conceptual idea of it. The electric field of a source charge Q fills the space around it. So I can only draw this in 2 dimensions because I'm stuck on a piece of paper, but what you're supposed to envision is radial lines coming out from that point charge in all directions, X, Y, and Z, and then filling the space. I'm only drawing a few representative lines, but they would be, every direction, all radiating out from this positive point charge here, Q. And this source charge Q has altered the space around it, creating this electric field E. To summarize, this is my 2 points. And now, once we've altered that space around the source charge, if I come in with a small charge, small q, and it's in that field, it will experience a force exerted by the field. So we've introduced this middleman, this idea of an electric field. Now, how do we calculate this? How do we get the magnitude of this new creature, the electric field? Well, I'll give you the definition here is that we start with Coulomb's law for the force, and the electric field is defined in terms of that electric force, except what we normalize out, we divide out, we take out this small q. So I want to think about, okay, I have this source, I bring in a small test charge q, I figure out what the Coulomb force would be, and then once I've done that, I divide out the q. I know it sounds weird, but bear with me. I hope to try to convince you that this makes sense in a moment. So this is our definition. You start with Coulomb's law, you divide out the small q. Let me give you an example. So we have a point charge. If we have a point charge which has, some charge on it, large q, and all around it, it has created an electric field. That's what I'm asking you to envision. It's modified the space around it by the fact that it has a charge and the space is modified in some way. Then at some arbitrary point in space at a distance r from that point source, which I'm signifying by by a point x, y, and z. If I want to know what is the electric field strength at that point, what do? Well, I have to mentally think about if I brought a test charge in here and I put it at this distance r from the source is what I'm interested in here. I could then calculate the electric force between those two by just k q over r squared. But this is just a bookkeeping device. The small q is just so that I can evaluate the impact of this big Q on the space around it. So my force is q over r squared, but I don't care about this test charge. It's imaginary. It's just a bookkeeping device. So I normalize it out. And in the end, what I get is that the electric field due to this source charge here, which is what I'm interested in, is that Coulomb force divided by the small q. I've gotten rid of that imaginary small q, and I can just calculate it by the magnitude of the source charge, the distance to the point in space that I'm interested in, and then Coulomb's constant, and that's distance is squared. There's a convention in this, in that if I have a positive point charge, it points away from the charge. If Q is positive, then the arrows point away. If Q is negative, then those arrows are going to point in towards the source. And I'll open this up for questions in just a moment, but I want to show you, some evidence that this is not a ridiculous idea. I don't expect you to believe it right away or to register it as deeply as possible right away. But what I have here is just a little experiment you can set up at home if you have some way of charging things. This is a pan of oil, a thin pan of oil, with pepper just sprinkled on the surface of it. And then we introduce 2 positive point charges in this pan of oil. And what we find here, again, it's an analogy, so it's not perfect. But what you find is those field lines, the pepper aligns itself along those field lines, and we see this radial distribution of field lines coming out from the point charges, right? In the middle here, where these two, this is a vector quantity, so you're going to have some vector addition of these two. I don't need you to know much about this right here. I just want to explain why it's a little bit messy in the middle, is because you have a vector addition of those 2 electric fields. The opposite of this is if I have a plus and a minus, then those electric field lines are going to come out from the plus, radiating outwards. And again, it's pepper and oil, so it's not a perfect analogy. But you can see that these lines come out from the positive, and we have lines coming into the negative. And what's interesting is you find these field lines that go from the positive to the negative. That's the last part of our graphical convention, is that field lines always originate on positive and they always end on negative. So we'll put some numbers into this, and I'll try to make it a little bit more concrete, but I wanted to introduce this concept just so that you've seen it. And the last part of this is this particular configuration of a positive and a negative is known in physics, in electrostatics, as a dipole field. So the resulting electric field lines, this kind of interesting distorted shape going from positive to negative, is known as a dipole field. And we'll come back to this because it has some pretty neat implications for biological systems. So I'll stop there. If you have any questions or you want me to rewind to anything, I'm happy to do it. I hope that Dawn and I will be able to post these by noon today. Thank you for your patience, and please do keep giving Dawn and I feedback on what's working and what's not working. If you think I'm going too fast, or if you think I'm going too slow, that kind of stuff, or if you can't see my notes, please let us know. So do we have any questions about any of this? Where do the lectures get posted? Dawn, you want to field this one?
On Canvas, under modules, under lectures. So we have the notes from Monday on there, and we'll have the notes from today. That can get up there soon.
Okay, Stephen, I get what you're saying, and no problem. Thank you for your answer.
Owen, did you want to add to that? You said 2 things.
2 things.
Ah.
Oh, yeah. Okay. Is it possible for you to go a bit slower? Yes. Thank you. That's exactly what I need to hear. If it is too fast, I will try to go slower. I appreciate it. Owen is asking, yes. Can I go slower? And I will try to go slower. And the second one is what? Maybe he's asking me to put velociraptors back up. I'm not sure what Owen's second. Is it possible for you to install some app that will let you write it out for us like it was a lecture at school? Excellent suggestion, Owen. I really want to do that. I don't want to use, this kind of canned notes. The problem is Zoom does not do that for me. They have this whiteboard, and I really like Zoom. I don't want to put it down, but the whiteboard feature is not good. I can't do that until I get a, yep, like Khan Academy. I get exactly what you're saying, Jacqueline.
I think what Carl really,
yeah.
Sorry, I think what Carl really needs is a tablet. I don't think it's an app that he needs. I think it's the hardware, and I'm not sure we can get that at this point. So, or we can look into that.
Yep. I absolutely see the limit that you're pointing to, and I want to fix it. I just don't have the resources to do it yet, Owen. I'll try to.
There's also a question about, is group work still graded on completion or accuracy? It is still graded on completion.
Okay. And we get, thank you, have a good day, thank you. And Peyton L, thank you for sending the Velociraptor photo.
I think she really liked the puppy pic.
She liked the puppy pic? All right.
She did.
Let's go out with a puppy then. Okay. All right. Thank you, everybody. And Dawn, are you going to, you're going to use this same link on Friday for group work, or are we going to use a different one?
I'm sorry, can you ask that again? Oh, a different,
The Zoom link. Are you going to use my Zoom link on Friday?
no, it'll be a different Zoom link.
It'll be okay. So stay tuned to Canvas, and Dawn will post a link for that. Thank you, everybody. Have a great day.
Ciao.
Jacqueline, you're very welcome.